But you need to, in order to identify building age, you also need some building age data to train your model, and this is difficult. So the main goal is to use existing data to create a transferable model. And this is what I called create model in the presentation yesterday. So we want a model that can be transferred from existing cities to new cities with minimal amounts of data. Okay, this is an example of transfer learning. Okay, I hope everybody did have a chance to. You do all have access to the notebooks, yes? Yeah. I hope everyone had at least a few minutes to look at this. Okay. All right, 4 age classes. The satellite data has 40 years of data from 1984 to 2024. So we have 2 classes during the time of satellite observation, and then we have 2 classes before. The 2 classes before are demarcated by a significant event. And that significant event is determined by that city's individual history. So if we applied this to a different city, we would choose another different significant event, right? So we want to have 4 classes. In fact, the 4 classes could be arbitrary. The point is that we just want to be able to distinguish data into 4 classes. And if you get a new model, you will retrain those 4 classes to be appropriate to that city. Okay. All right. So let's see. Okay, let's see. All right. So, there's some technical details here. Okay. So the submission requirements. So you will receive Madrid training and Amsterdam transfer. And I emphasized yesterday that you will use only the Madrid data for training. And the Amsterdam data is more for validation and to see how well your created model work. Okay, so use Madrid data to create a transferable model. Then in order to evaluate the accuracy of that model, you will use cross-validation. So we will see examples of this in Notebook 4. Okay, so I think that you can certainly reuse a lot of the code in the 4th notebook, right? So you don't need to write all of this code from the beginning. Also, of course, you can ask Claude to write code for you. Claude does a very good job of writing code, or ChatGPT, or there may be some others, or even Gemini or Copilot can all write code. Okay, so from this Madrid model, you will develop a transfer procedure that takes the model and uses a small number of labeled Amsterdam pixels to produce a model for Amsterdam. And again, in Notebook 4, we will see an example of how this works. Okay, and then you will use the Amsterdam data to evaluate this transfer. So you will not just do this transfer once, but you will do it many times and get a distribution and find the mean and standard deviation of the transfer model accuracy. Okay. Okay. So you will do, so for deliverables, the trained model from stage 1, a training code that adapts this trained model to another city, in this case Amsterdam, a PowerPoint presentation, and written justification. All right. Scoring, I don't think we're going to be scoring here, but this is just for this may be revised before you run your hackathon. We'll have to see how this goes here. But this is kind of a dry run to perfect the different aspects of this hackathon. Okay. All right. So the data set is Parquet files. I guess they're in this notebook data here. You can see, I don't know too much about the Parquet format. It's just an efficient way of storing data. And why did that happen? Oh, okay, I see. Okay, all right. All right. So essentially, let me not go into this in too much detail, but you should read about how the data is formed, and the 2 cities. You give some background of the 2 cities, and again, we want a city portable model. Okay, and I hope you read this also. So let me stop here and ask if there are any questions on this on this first notebook. Is it clear? Everybody, anybody awake? They should all have lots of coffee. So, right. So this is the easiest notebook. It gets harder. So prepare yourself. All right. So this is the background of the problem. Reading data. So again, this is more technical details. You will just use this to read your data, but there is some aspects of, and I believe that this will run out of the box. So I think you can just run it on your platform and it should run without any trouble. Now, apparently, some of the notebooks take quite some time to run. But we'll see how that works. Okay. Right. So here we can see some characteristics of the data. You have, here we have, actually we have 3 million rows. Now, that doesn't mean that there are 3 million pixels. What that means is that there are few, because each pixel has 40 years of data. So you basically need to divide this by 40 to get the actual number of data points. Right? We're tracing one pixel across 40 years, but each line here, you can see each line here has a year. So when we create the data vectors for our model, we will be concatenating vectors from this data set. We'll trace one pixel across all 40 years. Now, this is not divisible by 40, and I think that's because in some years you might have some missing data. All right. Oh, here, sorry, this is what it says. 76,263 unique data pixels. So really, that's the amount of data that we have. Right. You can see the age class distribution. Does anybody have any comments on these numbers? People who have experience in data data analytics may notice something about this. Yes. Yeah, there's a this. Yeah, okay. You want to explain what class imbalance means?
It's an even number of examples in each class, so that it can skew the user evaluation metric. It may not actually be a set of calculated. It might sort of false impression.
Okay, all right, excellent. Okay, so let's keep that in mind, that there is a class imbalance. You see which class has more data? Class 2. Class 2 has almost twice as much data as class 1. All right. So let me just say here is that there is no need to use all of the data. You can, for instance, you could simply decide to take the same amount of data from each class. There's no need to use all of it. You should use a lot of data, but there's plenty of data there, right? And we will see later on that this class imbalance does cause problems. It causes significant problems in the estimator. Okay, so here's just a list of the, this is not the complete data, but this is some aspects of the data. So you can see it has the city, it has the, it also has the, so this is just the total, this is just the complete ID, but you can see it does have a pixel location, the X and the Y. Coverage means what fraction of that pixel is actually covered by buildings. Then the year is the mean year of buildings in that pixel. That's the date of construction, the mean date of construction. And then these are the spectral values. So we have different spectra. These is visible light. I don't remember what these are. This is a measure of the pixel quality. And let's see. And there are other things to identify the satellite and so on. Okay. So we have one of these for each pixel, for each image. For each pixel, for each image. Okay. Sorry, I neglected to say, I believe there are 3 images per year in the original data set. I believe there are 3 images per year. This next cell is a screening cell. In the preliminary data analysis, we did find one image that was an outlier. And this happened because there was cloud cover that that was not detected in the original filter. So we took this out manually. Now, remember somebody had a question about the processing that we did to create this data set, and maybe we can, there are those Jupyter notebooks. I think we can make those available to you. Those will not be used in the hackathon. But if you're interested to see how this data was prepared, I think we can make that available to you also. I can just zip them up and put it on the chat as well. All right. So this is simply saying that we did find one image that was not when we did some graphs, there was a big spike, and we discovered that there was a problem there. So this is a lesson to me, and I think it's a valuable lesson that whenever you're working with data, you should always try to represent graphically what's going on with the data. You try to understand it, try to become familiar with it, because you may find some problems. All right, so next one here. So now we do the same thing with Amsterdam. So Madrid and Amsterdam are loaded in a similar way. Amsterdam has somewhat less data, but that's okay because we're not using Amsterdam to train. We're only using it to adapt or to retrain. All right. This gives you a key for the different fields in the data. Okay. Okay. So the flat view takes one reflectance value per row. So there are 3 observations. That's all right. So I believe each row has 3 years, but we only select one. This was a choice, and there might have been other choices, but this was a choice. All right. So these graphs here are not really too relevant, but they are interesting. It's good to understand the characteristics of your data. All right, so building coverage distribution. So let me see. Does anyone understand this? What do you suppose this graph is showing? It's a coverage distribution, right? I think now I'm sorry that I am the professor, so I have to go into professor mode. So one of the things I try to emphasize to my students is it's very important to be able to understand graphs, and you can understand graphs just from the numbers that are on them. Here you can see that this X scale is from 0 to 1, right? So 1 should mean total coverage, 0 means no coverage. And then here you have percentage of pixels. So this is definitely a histogram. And then we have these bars here. So, and we're looking at pixels, okay? So we're counting pixels, right? And we're counting percentages of pixels, right? So if I, if I added up all these bars, what number would I get? Right, this one says 8, 8. This is, I don't know, this is 9, 8. This one looks like 9.5. If I added up all these numbers, what would I get? 100, right? It's a percentage graph. They're just trying to get you woken up, okay? So no grade, it's okay. Okay, all right, so, all right, so we can see here, suppose I have a pixel in this category at 1. What does that mean? What does that mean about the buildings in that pixel? It means that pixel is entirely covered with buildings. Right. Now, one down here means only 20%. of the pixel is covered with buildings. Maybe there's a yard, maybe there's some water, maybe there's a parking lot, maybe there's something else. Okay, so not all the pixels are filled with buildings, but we only select pixels that have, sorry, a minimum fraction. Looks like 15%. So we pre-screened and we removed any pixel that had less than 15% building in it. Okay. And you will see that in some of the pictures. You will see a lot of gray pixels which were removed because there was not enough building in that pixel. Right. So we can see here, this line here is the median, and this line here is the mean. Those are two different statistical measures. Median means 50% below, 50% above. Mean means you take the average. Okay. All right. So if we compare Madrid and Amsterdam, so this is Amsterdam. I don't know if I can put them both on the same page here, maybe. All right. So you can kind of see, I think make it down a little more. Okay. So let me ask you, which city is more densely covered with buildings? Yeah, Madrid is significantly more, the buildings are significantly more densely packed, right? By this much. This one, the mean is 42. This one, the mean is 50. So almost 8% more, right? That's not really relevant for classification, but it does tell you that these different cities have different characteristics, right? So this also shows us that our data is reasonable. That's not an unreasonable result. All right, let's go back up. I think I'm probably going to have to speed up. I see, because I should spend more time on the relevant stuff. All right, so so here we see the different class distributions. Once again, here we can see the class imbalance. There's more in class 2 than in other classes, especially in the Madrid data. And these are pixels. So you may want to equalize the data. That might be a good strategy. And then here is a more detailed view of the years. So this is histogram according to year, and you can see here there's a spike where a lot of buildings were built during this period from just before 1984. Okay. Now this one is. You remember what we're trying to do. We're trying to trace one pixel over time and discover from the changes in that pixel value which class it belongs to. So each year that pixel is going to have a different value for its reflectances. And we want to look at those reflectances and discover what class that pixel belongs to. So it's good to take some examples and see if you can distinguish visibly between the four different classes. So the strategy here was to plot some examples from each class and to see if we could visibly tell from the picture which class the pixel is in. So that's what these graphs were for. Let's look at some of these graphs. Okay, so hopefully you had a chance to look at these graphs. So I'll pass this over and get to the graph. All right, so here we have, all right, now what is this showing? It says, at the top it says blue over time. Can I make this bigger? Well, I guess it's okay. It says blue over time. What does that mean? We have several spectral values here, blue, red, green. We also have SWIR. We're just looking at blue. So this is one reflectance value. It's looking at the blue light quantity from that pixel. And we're looking at that blue light quantity from pixels from each year. These three lines represent 3 pixels. These are 3 pixels that all come from this class. Right. So you can see that there's some similarity between those 3 pixels. They all have sort of similar range. They're not identical, but they have similar variation, similar range. These are 3 pixels from class 2. Right? Now, you do need to be very careful when looking at data like this, because your eyes can see patterns. It's like when people look at clouds and they say, there's a lion, there's a map of China, see, these are patterns that your eye makes. But sometimes there are some suggestive things. Now, if I were going to compare the lines here and the lines here, what would you say, is there really a significant difference? What would you say is the difference between those? Just in general. You see any characteristics in this group of 3 pixels that you don't see here? Well, what would you say? Yes. All right. Yeah, this one actually seems to have more spikes, doesn't it? Now, that may be an artifact, but it may be significant. It is something to think about. It looks from these 3 examples that class 2 is more variable than class 1. So that's something to keep in mind. Any other difference?
Yeah, that's great.
All right, well, let's look at 1 and 2 first. Yeah. I don't know, but would you say class 2 is a little bit higher in general than class 1? Maybe a little bit. Again, this may just be because I'm looking at only 3, but that is suggestive. That might be something that distinguishes those 2 classes. Yeah, it is on the same scale. And they look, I mean, you should not compare blue here with blue here. There's no relationship between those 2. Those are completely different pixels. But these do seem to be, at least it looks to me, perhaps a slightly higher in average. Okay, so that's also suggestive. All right, now let's look at class 3. Now, I should tell you that those dotted lines are the actual date of construction. Okay, so this orange dotted line indicates that this orange pixel was constructed in this year. The green indicates that the green pixel was constructed in this year, 2004. Okay. So do you see any significant features here that you didn't see in the other ones? This actually looks, yeah, it does seem, it may be significant that near the year of construction, this one does have a sharp increase. All right, that might be significant. Okay. Another thing that, again, your eyes may be taking tricks, but it does seem that there is this downward trend. Okay. Okay. So that's a possible distinctive feature, possibly. Okay, so you can look at these more in detail as you want, but the purpose of these graphs is to identify possible features that might distinguish between the different. Okay, but you can see from this graph, this is not going to be an easy task. If you give me one of these lines and say which class, I can't tell. So this is good. So we're really asking a great deal of our algorithm. We're asking it to do something that we ourselves cannot do. Okay. Yeah, question?
So when choosing the pixels from God, did you consider the fact that they have different colors?
No, we did not. I did not. Just chose 3 random ones. That's true. That's a very good point. I did not consider that. That's extremely good. That's a very good point. So the coverage fraction may be useful to include in your calculation. I did not think of that. Yeah, that's an excellent point. Okay. All right. So they're more like this. This is Amsterdam. Okay. So that's the purpose of these. I don't want to spend too much time on that. This is a different spectral band, NIR. So you can also do this. So, all right. And SWIR. So these are all just things for you to look at. Okay. Now, what these are the mean reflectance over all years. No, sorry. For this is the mean reflectance for each year for the different classes. So, for instance, this point here, this red point here, what year is that? Maybe 2000, it looks like 2002. So this red point here, what is that? We took all pixels in class 4, we took their mean reflectance, and we took the average. Okay. Now, what are these shaded regions? Well, this is a standard deviation. So that's the variation within that year. Of course, not all pixels have the same value. There's some variation. Okay. So the red is class 4, the orange is class 3, the green is class 2, and the blue is class 1. So what do you notice? Yes.
I think now it's clear that they have a different difference because the clip that the red is up.
Yes.
And it's consistent throughout this.
Okay. Yes, the red does seem to be significantly more. And in fact, what's another point that's interesting is that for earlier years, you don't see a difference. But for later years, the difference becomes like for earlier years, it's basically identical with orange. But then for later years, it diverges. Okay, so that's a good thing. What about the shaded regions? For instance, look at this up here. What does that mean? Someone from this table. What does this red shaded region up here, what does that mean? Remember, the shaded region, the upper edge and the lower edge of the shaded region is plus or minus 1 standard deviation. So you do need to know some statistics here. Plus or minus 1 standard deviation. So standard deviation measures how variable. So if you're looking at this graph, which class has the highest variability? Yeah, class 4 definitely has the highest variability. Highest mean, highest variability. Okay, so those are two aspects that might be distinguishing features for class 4. And that's per year. That's per year. Okay. And then this Amsterdam, actually, you see something very similar for Amsterdam. All right, and this is a different band. The first one was blue, this one's NIR, et cetera, et cetera. Okay. Okay, so different band, okay. All right. Okay, so this is a different way of representing the data, of the same data. This is showing the distributions. Let's see. Is that what's down there? All right, so this is over all years. This is averaged over all years. And once again, you can see the higher variability for red. So this is encouraging because it is showing that there may be some way to tell apart the different pixels. Showing in the different bands. And then this is the year-on-year change. What does year-on-year change mean? Year-on-year change means I take the data from 1984 and subtract it from, I take the value of 1984 and I subtract it from the value of 1985. How much does it change between years? And I take the average of that. So that's another thing that may be useful to look at. Okay. And then And then here we plot mean versus standard deviation. So I should just say that this is just, you can explore this. This is just some way of exploring relationships between the different features in the data. Okay. We're measuring 6 different types of radiation. But it turns out that some types of radiation really are almost the same. This one says blue, green, and red basically are giving you the same information. It does say blue, green, and red is quite different from SWIR1 and SWIR2. All right, so summary. Okay, so the purpose of this was to look at the data and see some of the characteristics. Any questions? Okay, I think I am going to make it in time. Right. All right, so based on this, we want to prepare the data for analysis. So we do want to construct one data vector for each pixel. Right now, we don't have that. We have a data vector for each pixel for each year. But we want to have a data vector for each pixel over all years in order to predict the class for that pixel. So that's what this is doing. We also want to take our different measured values and create features that reflect the differences that we've seen in Notebook 2. Okay. So we have imports. We load the data. We assign the classes so that we know we can associate with each point the class that it's in. We simplify to one observation per year. And then we fill in missing data. So sometimes you may have, for a given pixel, you may have the data in 1992, and the next data point is in 1996. And we have some missing year. So the missing year's data is filled in using the near interpolation. Okay. All right. These values are derived from the spectral values that are actually measured. And this is from the literature. The literature says that these values are useful in determining built-in features. Okay. So you can see that these values here are the values that are actually measured. And these are what are called indices that indicate characteristics of the reflecting object. And here it says that these actually relate to different things, that this captures vegetation, this captures build-up intensity, urban areas, et cetera, et cetera. Okay. So this is from the literature that urban planners have used. Right. So these are added to the data. Okay. All right. So here it says this is the most important section. As I've been mentioning, each pixel's time series up to 40 annual observations is collapsed into a single vector so that we can use that vector for prediction. Okay. So we want to see how the spectrum changes over time. Okay. Okay. All right. So, all right. All right. We had this already, so that's fine. Okay. Then in order to compare across years, we use standardization. We put all the pixel values on the same scale. And then here we save the data. So once you've done this, then your data can be accessed. You don't need to reprocess. So you should be able to run this notebook once. Now, you do not have to use this feature vector. You can modify the feature vector that you use. You may decide to use a different set of features. So don't feel that you have to use this data. You just think it is a good starting point. But, you can decide that you don't want to include something, or you do want to include something else. Okay. Last notebook, we're almost there. Okay. All right. So in this notebook, it talks about the particular. Oh, sorry. Do you have any questions on notebook 3? I'm sorry, this is a lot to take in, but you have 2 days, and you have people you can discuss with. So I'm confident that you will be able to do this. Questions? Right. All right. This is in this notebook. We give an example of one possible approach. So this notebook you should completely rewrite. You will make your own version. Use a different technique. You may modify this one, or you may start with use a completely different technique. Right. All right. So in this one, we do follow these steps. First, we train on Madrid. We take a classifier, a standard classifier, and train it on Madrid. Then zero-shot transfer. What this means is that we use exactly the same model on Amsterdam to see how well it does. And we actually do not expect this model to do well, because Amsterdam should be different from Madrid. But this is for comparison purposes. Certainly, we do not expect a model to work on a new city. Then here we have this transfer learning, this transfer where we do some small retraining so that we can use the Madrid model on Amsterdam. Okay, so it's like some small adjustment. It's like I was telling somebody yesterday. If you learn to drive in Kenya, then your driving is you're on the left-hand side, right? Then you come here and the steering wheel's on the right-hand side. Okay. Do you need to relearn how to drive? Well, not completely, but you do have to relearn some things. So that's what this few-shot transfer is. It's taking a model that has been well trained and making some small adjustments so that it can be used in a different city. So that's the idea. We always have setup and imports. We need to load the data. We verify that everything is there. Then cross-validation means that in order to get the accuracy of the model on the grid, you should not just do it one time, because when you use machine learning, there is some random variability. You may train the model and get 60% accuracy, but then you retrain and you get 55% accuracy. You want some idea of how much variation there is when you, according to these random effects. Okay, so we actually do. It says n folds and n repeats. So what we do is we do training on 5 different sets, 5 different times. So n folds is the number of different sets that subsets that you're training on. N repeats is the number of times you retrain. And you can see down here, okay, and this macro F1, and this macro F1 is a measure of accuracy. So you can see it's not always the same, but the different values are quite close. I can see the 0.61, 0.62. So it's all around 61, 62%. And here's the summary. It's 61. It's 61.79 or 0.6179 plus or minus 0.0043. Okay. So the values are quite constant. Okay. So we have a very good idea of the real accuracy of this model. I say accuracy, but a macro F1 is very similar to accuracy. And here's this is just a graphical representation of the same variability. Now, this one on the right I like this diagram very much. And I think it's good to take some time to understand this diagram. This is called a confusion matrix, and that doesn't mean that you're supposed to be confused by it. It's supposed to tell you how your classifier is doing. And it gives very detailed information about how your classifier is doing. Right. So for instance, let me see if you can, so we've seen confusion matrix before. Few people? All right, this is really a crash course for many of you. Okay, all right, so suppose that I have a pixel in class 3. What is the probability that it will be interpreted as a pixel in class 2? So the building is actually class 3, but what is the probability that the classifier will think that it's in class 2? Sorry? Yeah, that's exactly right. That's exactly right. He said 0.33. Do you see it? Okay. This one says the actual class was 3, but the predicted class was 2. So this value is 0.33. So that means 30%, 33% of the time, the class 3 pixels were wrongly classified as class 2. It's confusing class 3 with class 2. On the other hand, if I have a pixel in class 2, what's the probability that it will be predicted to be in class 3? 0.08. Okay. So there's a lot less confusion the other way. Only 8% of class 2 pixels are wrongly classified as class 3. Right. Let's see. What's the probability that class 1 is correctly predicted? Okay, 39%. Right. So these diagonal entries are particularly important. Okay. Which class is classified the best? Class 2. Which class is the biggest? Do you remember? Class 2. Class 2 is the biggest. And class 2 is the best predicted. This is not an accident. This is a problem. This means that your classifier is favoring the biggest class. Okay? So this is a problem. It's not and you can also see that class 2, that other classes are often mistaken for class 2. Because the classifier favors the biggest class. So this is an indication that these imbalanced classes should be balanced before you do your training. All right, so that's a problem. Okay. Now, on the other hand, this is rather encouraging that you have, well, except for the first class, it's really not surprising that these two classes are often confused. Why? Because class 1 and class 2, there really is no change during the period of observation. So it's really not surprising. And perhaps we can improve this by balancing class 2. Right? So that's an encouraging feature. And this is also quite encouraging. Oh, you're over 50% accuracy on 4 classes. That's really not bad. I mean, random accuracy would be 25% across the board, right? If this was just a random classifier, everything here would be 0.25. So we're not bad. This is not bad. Okay, very encouraging. Now that's Amsterdam. That's Madrid model predicting Madrid. Now, when we use the Madrid model to predict Amsterdam, do you expect that to be better or worse? So of course, it's going to be worse. Okay. Right. Now, I like this graph very much. What this graph is telling you is it's actually keying your accuracy to the location. Fortunately, we have 4 classes. And the way the 4 classes are assigned to colors, one is red, one is blue, one is green, and one is black. And the classifier will assign a probability to each pixel. I'm sorry. The classifier will assign a probability to each class. So for one pixel, if I have one pixel, it's going to tell me. So for instance, if I have one pixel. I have one pixel here. And then I'm looking at that pixel across all years. So that pixel is going to start. So that pixel is going to have it's going to have a probability of 1. It's going to have a probability that's in class 2. It's going to have a probability that's in class 3. It's going to have a probability that's in class 2. All right, now suppose this probability is again, I'm sorry, being a professor. Suppose that probability is 0.5. Suppose this probability is 0.15. And suppose this probability is 0.2. What is the probability? Of this one? Yes. Exactly. So you take the sum of these and subtract it from 1. So I believe it's, what is it? So that's 65, and then there's 85, so this, I think it's 5. Is that correct? Something like that. Right. So if I know 3 of the probabilities, then I can find the 4th one. Right. So what I can do is I can represent these probabilities using colors. Okay. So I'm going to if this is 0.5 to 0.5, I'm going to make a pixel that's 50%. That the red intensity is 50%. The blue intensity is 15%, and the green intensity is 22%. So the pixel is going to look quite red. It's going to look very red. So the pixel color will reflect the class. Right. And how close the pixel color is to the actual color reflects how certain you are. All right, so it does, I think it really is worth time to take a look at these graphs. So this is Madrid. So I think after seeing this picture, everyone wants to go visit Madrid. It's a beautiful city. Okay. All right, now the graph on the right are the actual classes. Now, what are these gray pixels? These gray pixels are ones that were thrown out, right? Either there's not enough building, or there's water, or it's something, okay? So the only pixels that you care about are the ones with color, the ones that are green, red, blue, or black. Now, when you're looking at the actual classes, these colors are exactly one of those 4 colors. I can tell you exactly, like for instance, this pixel here, that's a green pixel. It's fully green because that is the true class of that pixel. Okay. Right. Now, so this is the distribution. And one thing to notice here is that they're very distinct neighborhoods. Like this is definitely because class 1 is old, this is definitely the old quarter here. Very distinct. There's some other ones there, but almost completely one color. Okay. This one here is very clear, completely blue. Right? Okay. And you can see that this is quite a common pattern. There's some mixture, but you are getting you can say these patches of solid color. Now, this is the classifier over here. Right. So I hope that's big enough. Now you can see that it's really pretty good. The colors are matching quite well. You do get some mistakes, like you can see there's quite a bit of red mixed in here with the blue. Okay. And the colors are not matching exactly. But we are getting the general pattern. This is really quite encouraging. And this is why I said that perhaps you can take your initial classification and then try to improve it based on location. But this is a very encouraging result. It's showing that we are classifying quite well. This next graph is showing you how certain you are. Okay, how bright the pixel is let me see. Why are there two here? I'm trying to think. Why are there two of these here? Yeah, they're both the same. Oh, I see. They're just two different measures of uncertainty. What this is saying is the classifier, when the classifier makes a classification, it is not it's not sure what the right answer is. It's not, the classifier doesn't say, oh, I'm certain this one is black. I'm certain this one is black. The classifier assigns some probabilities and then makes a judgment. Now, if the pixel is bright, that means the classifier is quite certain about the result. So you can see these two different measures right here in the old quarter. It was very certain about the classification. Let's see. Yeah, bright is good and black is bad. So you can see that over here, in this area here, the classifier was not certain at all because I'm getting dark pixels here. So this is telling you where the classifier is having trouble and where the classifier is doing well. So this information may also be useful in designing your classifier. All right, so that's Madrid. Okay. And then this one is plotting the correct pixels and incorrect pixels. Here, the red and black is just marking correct and incorrect. I think black is correct. I don't remember. Black is correct, red is incorrect. So we can see there are a lot of incorrect pixels spread throughout the image. There are a lot of them, but they're kind of scattered. Okay? We're getting some correct, and there's some areas where it's quite good. Like in here, it's very good. Down here, it's very good. There's some areas where it's having trouble. Okay? And then these are showing here the colors here. The yellow are the incorrect ones, and then the correct ones are mapped according to color. So I don't know. I like graphs maybe too much. Okay. Okay. Now, what this is looking at is in each data vector there are different features. And so, for instance, in here there's I think you have to look in the notebook more carefully to see what the features are. These are showing you how important the different features are. All right. And I have 1 minute. Okay, so I don't know if I'm going to quite make it, but I think we'll make it almost. Okay. All right, so then this here is showing the same model on Amsterdam. All right, how good is this model doing? This model is awful. It's predicting everything as class 2. Once again, this is your class imbalance. Okay, it's predicting everything as class 2. Right. But this is using exactly the same model on Amsterdam and Madrid. Now we apply the retraining. Okay. And we only use a few points from Amsterdam to retrain. And just to go down there and see the result. Okay, yeah, you can see that this result is bad. So this is Amsterdam now. Okay, this is Amsterdam. All right, so now we're doing some retraining. By the way, if you look into the details, the classifier that I'm using here is random forest, and all I did was type in one line random forest. You could replace that with any classifier. You could do SVM, you could do XGBoost, you could do some other classifier. I just made some random forest as a choice. Okay. All right. So this graph, my time is limited. So what this graph is showing is that if I retrain with, I think this is 5 points from each class. The accuracy is not too bad. This is the accuracy with no retraining. It's the accuracy on Amsterdam with no retraining. If I use just 5 points from each class, there's a huge improvement. And the improvement increases until I reach about, let's see, it looks like that's about 25 points. 25 points from each class already, I'm very close to 60%. If I do 50 points, I'm close to my best result. So just think about the implications here. On Madrid, I had over 3,000 points per class. Now I'm only using 50 points per class. Right? You can ask someone to go out in the city and identify 50 pixels, 50 points for each class. That's only 200. That's only 200 pixels. So on 200 pixels, it's doing 60% accuracy, which was the same accuracy that Madrid attained with 10,000 points per class. Okay. This is quite impressive that we've reduced the work from 10,000 per class to 50 per class. You can do the math, how much that is, how much that 200 times less data. Okay. And then here you can see the confusion matrix. Once again, these two classes are highly confused. These two classes are somewhat confused. Class 2, again, is being over-predicted, but this really is not bad. So this is what I want you to do better. Okay, you can do better than this. Okay, and these are the same plots for Amsterdam. Okay, I'm 2 minutes over, so I do want to leave you a lot of time, and certainly I'll be going around, and if you have individual questions, we can talk about that. But I think
All right, right, I'm going to see your group and the login and password for machines. So you should, each group should sit together. I don't know, let's say this is group 1, right?
Yeah, I think
1, 2, 3, 4, or 3. And you should sit together and please check your login and password into the virtual.
So just make sure that you are all logged in on the same.
So look, that this table is group 1, 2, 3, 4. So go to table, with your teammate, and I just understand. 1, 2, 3, 4.
Hello guys, can you hear me? Are they all online?
Just check Nigeria, Ethiopia.
Okay, so Ali is the one who's replacing Salah, right?
think so. Can we check that the team, there is someone for Iraq?
Iraq is Ali, I think.
Okay, someone for Ethiopia? Ethiopia, can you just raise your hand?
Okay, Ali. Ethiopia? So no one from Ethiopia, right?
Okay, Nigeria? Is there anyone from Nigeria, please?
Logging in, we are just trying to see if we can get that fixed quickly and that's it.
Me
Yeah.
and Ali from why two people? Why two?
Come to that. And then Ethiopia, Nigeria, Tanzania, if you're here, please raise your hands or add in the chat.
Ram, we have the template that we're using at the screen as OED.
We've already given it to someone. Oh, that one.
The one that's the screen. I mean, it works.
Yeah, you can try that.
You just need a laptop that can log in, right?
Okay, so we're still missing Ethiopia, Nigeria, Tanzania. Okay, Tanzania we have, so we're just missing Ethiopia, Nigeria. All right. So you want to tell them just one person?
Yeah, so actually we only need one person from each team, supposedly the lead. But if someone is replacing the lead for today and tomorrow, they're the only one who should be joining the group. And this link will be on, right? It's the same link, right? Should we do another link for only the
team
leads?
leads, yeah. So we can create a Zoom link just for
work.
the one representative from each team. So we need one person from Iraq, one person from Ethiopia, one Nigeria, one Tanzania.
Yeah.
Please tell us in the chat who this person is and enter your email address and we will send you the login details for the virtual machines to that email.
While we're waiting.
Oh.
Oh, sorry.
Oh, yeah. Hi, guys. So while we're still trying to log in, I just wanted to make a quick announcement. I realized that my kids are going to be off the YouTube game, like the penetration program, and that's going to continue today and tomorrow, right? So what we've decided on is
Okay, we still need the email address for Ethiopia, Nigeria, Tanzania. The other teams have started working, so please give us this email address as soon as possible. Okay, so we will send you the email in a minute. Okay, Ali and Yona, we have sent the login details to you, including the link for a different Zoom meeting. So please join that Zoom. We will close this Zoom in a minute. For everyone else, we will close this Zoom. So if you are not a team lead, you don't need to be present. Is there is anyone from Team Nigeria, please email us. We need to know who will be joining the hackathon challenge. So we will close this now. Thank you.